Good afternoon, everybody. Thank you for joining the webinar on simulation-aided design of magnetic actuators. I'm Nirmal Patil. I'm the lead engineer at Burst. And a little bit about my background. I'm an electrical engineer by degree. I did my PhD from UNC Charlotte, North Carolina in 2012. After the graduation, I worked for Consol Multiphysics, a software company, for 4.5 years as an application engineer and team lead. And then later on worked for ABB as a principal scientist for a little over 4 years in instrument transformer and sensor division, designing the outdoor products. Now at Burst, I'm the lead engineer responsible for mostly the multiphysics simulations, primarily focused on electromagnetics and thermal designs. All right, so the little bit on the housekeeping side, we expect you to type in questions if you have them. Please use the chat feature and send the message to the presenter here, and I will address those at the end of the session here when we have the Q&A session. And please also note that the webinar will be recorded, and for those who have registered, you will receive the link for the record. The agenda for today, we'll go briefly about what adverse engineering is. We'll introduce electromagnetic actuators and their applications. And I'll also discuss about the electromagnetic modeling workflow, specifically in Consol Multiphysics package. And we'll go through different examples on voice coil actuators, solenoid plungers, and I'll do the live demonstration of one of the example on the power switch using Consol. And finally, we'll share some of the design tips and considerations for designing those devices, and we'll take questions. First, we are a consulting firm based in Massachusetts near Boston, headquartered in Needham, founded in 2006. I currently have 16 engineers, out of which 80% of us are PhD holder from STEM University in the US. And we are also we also have a mechanical test lab, over 3,000 square feet space, and we claim ourselves as academic level expertise applied on the industrial timeframe. So you will see some of the our capabilities in the next slide here. So primarily, we're focused on the 4 different discipline or areas, starting from mechanical engineering. So mechanical engineering practice is, providing advanced consulting services for best material choices and their applications. And then material testing and material modeling for custom material testings where standard ASTM standards are not applicable. For example, for temperature-dependent, pressure-dependent, highly nonlinear materials for polymer, adhesive, and foams. And we provide multiphysics simulation software, services, consulting services, designing complex multiphysics problems for the real world. And we also provide services for failure analysis. Root cause analysis is in the core engineering discipline to evaluate different failure scenarios, usually for our legal and industrial clients. On the simulation expertise side, our expertise range from solid mechanics, fluid mechanics, heat transfer, electromagnetics, and multiphysics, and much more coupled problems. When they're highly nonlinear, customers reach out to us for the consulting services. We use various software that fits the needs for the applications. Abacus, Consol, ANSYS, or LS-DYNA. We are a certified consultant for Consol. And here are some of the examples, not the extensive list, but a few examples on the top left is the turbulent mixing of mRNA vaccine productions, coupling the flow with the chemical reactions. On the bottom left, we have a combustor liner heat transfer. It's a multiphase flow with the heat transfer. And then we have a Calorie Joule heating, coupling electromagnetics with the thermal physics. And then similarly, we have solid mechanics coupled with the fluid structure interaction on the top here, a flexible hard valve. And then we have a piezoacoustic particle focusing, coupling, piezoelectric with the acoustics physics, and then also with the particle tracing. All right, so on the material testing lab, we focus on non-standard and custom testing. And we work with every client to understand what they need to learn from mechanical testing, and we design customized plan to meet those needs. For clients requiring a data to be used in final element input, we provide the full suite of testing, material model calibration, and FEA services. So we provide a constitutive model for those clients to be used in the FEA. So here are some of the tests we support, fracture roughness, fatigue, cycling loading, DMA, and then also on the material model validation testing, we do a ball impact test, punch testing, and other custom tests. All right, to the core of the presentation today, let's start with the electromagnetic actuators, what they are, and how they can be used on different applications. So what is an electromagnetic actuator? It's a device that converts basically electrical energy into mechanical motion. It could be linear or rotary, using basically the interactions of electric current in the coil and the magnetic field produced by it. So there could be a combination of coil and a permanent magnet, or the magnetic materials. We'll see different form of electromagnetic actuator later on in the slides. But basically, they are governed by the three major fundamental physical equations: Lorentz force law, basically the force on the conductor carrying current in the magnetic field, described by the equation here, where force, we have the current, L is the length of the coil, and then B is the magnetic flux density. And then we have a Faraday's law of electromagnetic induction. A changing magnetic field induces an electromagnetic force. And then also the Ampere's law. We also have the equation that governs what is the magnetic field generated by the current carrying conductors. And there are also a situation where there is a force from those current conductors in interactions with the magnet. So now let's look at different types. People often call them, just a solenoid actuator. Some call it voice coil, linear actuators, rotary actuators, and some just various name for them, depending on the applications and preferred, industry practices. Typically, there are different types. So solenoid actuator, basically, you have a coil that generates a magnetic field, that moves the ferromagnetic plunger. So they're typically used in electric door locks, vending machines, and voice coil actuators operate based on the Lorentz force principle, provide precise force control, and they're used in camera zooming, high-speed speakers, drug delivery systems, and vibration control, where the speed is the key. And the linear and rotary actuators, they use electromagnetics to create linear or rotational motion, used in robotic arm, precision manufacturing, electric power switches, for example. This is one of the examples that we'll see how it's done in console later on in the demo. And then the electromagnetic relays, basically, they're used in circuit breakers, protected relays, aircraft, electrical switching, and many other applications. So when we are in the process of designing the actuator, right, we want to define the ratings of those. The ratings could be on various forms, depending on the applications here. Some of these that I have listed here are continuous power output. So basically, we want to specify what is the maximum force or torque that can be attained or obtained continuously without any, temperature exceeding the temperature limit. Similar to the range of motion, if it's the stroke length is 5 mm versus 10 mm or even longer, that needs to be defined. Similarly, for the rotation angle, the range is defined here. And resolution. So what is the minimum increment of force or torque that can be achieved? Similarly, for accuracy, you can obtain the motion, but is the motion linear with the response with respect to the input or not? That's called accuracy. And then also we want to know what's the peak force or torque that is achievable, and then the speed characteristics. If you're, for example, in the circuit breaker, there are certain requirements to turn on and off the vacuum circuit breaker, for example. You need certain speed to generate that impact. Similarly, there is a requirement for heat, and then also speed during load and not loaded conditions. So there are certain, it's not the actuator, but there is a combination of other mechanical equipments in it. There is a damper, there is a spring, there are certain contact mechanisms that create additional forces. They all need to be accounted, and the actuator should function properly in the combinations of those. And the frequency response, will we have to make sure that we'll get the linear response throughout the frequency of operation. For example, in the voice coil or the vibration damping mechanism. And also the power requirements. Are we supplying the DC supply or AC supply or multi-phase? What is the current level, voltage level, and so forth? So these are the performance. But now what are the design parameters that we have to achieve those performance? So we can play with many options here. For example, we can manipulate the magnetic field strength that determines the force output and efficiency. That means the force can be increased by the number of turns increasing, or the magnet aiding the magnets on it. There is a coil inductance of the resistance that impacts on the response times, and also in what is the power consumption there, and what is the available space on the design. And then type of the material selections for the magnetic core. For example, the higher permeability enhance the performance, but there are certain requirements for the cost as well. You have to be mindful on that. The air gap, which includes the reluctance of the magnetic circuit. Sometimes there are intentionally aided gaps, but sometimes we try to minimize those to achieve the maximum force. There are hysteresis, eddy current losses. We have to minimize those. And then, we always, as an engineer, we have to be mindful on the size and weight constraint, also on the material costs. So on the application side, there are a wide range of applications, but I've categorized here in consumer products, aerospace, power and energy, robotics, and medicals here. Some example on the top here is a voice coil actuator used in the camera lens. We have a lens 1 and 2, and then zooming is done by using the voice coil. And on the bottom one here is the actuator that's been used on the switchgear. So let's start the workflow of actuator modeling in COMSOL. So basically, whenever you're given a task to design any actuators, basically, so you have to first understand, the basic geometry configurations, and you have to decide whether you can, start with a 2D axis, or you have to start with a full 3D if there is no symmetry on the geometry. Then always, starting with a basic 2D or 2D axis symmetry is the best, just to achieve the first working model, and then you can move into the 3D if needed. And then the geometry can be built in within COMSOL, or you can import from outside from other CAD packages in different file formats. And once you have the geometry ready, then you assign the material to all the parts that are in the geometry. For example, there is a copper winding. There might be a magnet. You define the magnetic field strength on it. And also magnetic materials, you can define the BS curve, for example. And if there is any lamination involved, you can assign those anisotropic laminations by changing the permeability or also the conductivity. And on the physics setup side, you define different type of coils. If it's a solid piece of conductor, or it's a stranded multi-turn coils, there are different approaches to capture those in the software. And and then define the permanent magnet types. If it is a temperature dependent, or just a remnant flux density or magnetization, whatever is the quantity that's available. Pick the one and define all the boundary conditions, aid loss models, and so forth. The next step will be building a mesh. Basically, there is a automated mesh builder in the software, but it's always for advanced modeling or real world modeling, you always have to have some kind of customizations on the meshing to accurately capture the field. For example, eddy currents or those mesh sensitive quantities. Then the next step would be the analysis type. You can do the static analysis, you can do a frequency domain or time dependent studies depending on the type of problem that we're solving. Once you solve, boom, then do the post-processing results and do kind of 8 different physics to capture other effects. All right, so the problem that I will be talking today is as shown in the geometry here. So we have a 2-part stator outside, consists of a magnetic core and a coil, and then we have a magnet that's in the shaft side. So there is a shaft on the rotor, or actually the plunger. You have a magnet. There is a magnetic material ring, 3 rings, 2 on the top and 1 in the middle. So there is a design constraint here that we have a 2 ampere is the current that's maximum can go. There's a the height and the radius limit, and then also what is the target here is basically we want to achieve a 12 Newton force for a stroke of 5 millimeter. So we want to have a continuous 12 Newton or higher force when this the actuator is in a 5 millimeter stroke. And that's the case for both static and also the dynamic load conditions. And we'll model the additional spring and dampers on it, not physically, but mathematically by using the equations. All right, so as you saw on that geometry, basically we have a coil. Now we need to decide which single turn or multi-turn types, or if you are changing the wire to have a leads wire combinations, we can customize them accordingly. We mentioned that there is a permanent magnet, so we can choose different type of material for the permanent magnet type. And magnetic materials, we can always start with some kind of linear material with the permeability range from 100 or 1,000 or 10,000. But we can also include a nonlinear BS curve, or if there is a full hysteresis effect, that can be included. Mechanical parts, as I mentioned, will aid with a spring or damper with additional components. And often, we have a circuit that couples with the FEA model. So in that case, we have to do the FEA plus electric circuit couplings that can be done in console. So then finally, we introduce a moving mesh. Basically here, we have one part moving, another is stationary. So we have to be really careful on how we define that. For dynamics, we add global equations and multiplicity, or alternatively, you can also do this multiplicity dynamics. That's one of the feature in COMSOL. The optimization, we can always optimize for different things. For example, if you have a target of the weight, you can do that. But for here, we are choosing the force optimization. So we'll also how I set up a problem to optimize the force. And finally, if there is an additional need for coupling with a thermal, structural, fluid, or acoustics, those can be coupled. But all right, let's just start with a first. So we started with the stationary study on the 2D axis model, and then and then do a bunch of parametric sweep to calculate or to find the range of the performance of those parameters, and then move on to the time-dependent study using the full dynamics. On the time-dependent study, we include the nonlinear BH curve that includes the nonlinear behavior on the magnetic materials. So here is the animations, on the rotor side. It started from the bottom here and kind of slowly oscillate here. So it's still, there's some oscillations, but it's settled down to certain gap that is determined by the spring, attached to it. All right, as a demonstration example here, so this is a 2D cross-sectional view of the same, the device that I showed the animations. So on the beginning of the design, so we started with a basically shaft in the middle, and then we have a magnet pointing downward and upward, and then we have magnetic materials, kind of 3 disc stacking. And then on the outside, we have a housing that is also magnetic, and then a coil. But there is a slot, additional slot here, parameter A, and then there are parameter pole height, magnet height, and then the magnet radial thickness. So these are the parameters that are defined. We did a bunch of parametric sweep and see how the force changes for each of them, and found that these 3, 1, 2, and 7, these millimeter values seem to be the best combinations so far. On the next step, on the design, earlier we didn't have this notch here, so we introduced additional, teeth here, so that it can hold the magnet in place, so that it's easier for manufacturing and also for the structural integrity of it. So we added parameter B, and keeping everything else, and we keep changing or doing the parametric sweep again. Those numbers now change with slightly different values once B is introduced. So similarly, we keep doing that until we have some numbers, and once we have that number for the force, then we at the same time what we did is we introduce a global equation, which is mass, a damper is stiffness, and then equation of motion for it. That's how it's defined in COMSOL. And the above combination equation is split into 2 equations here, where P is the position, V is the velocity, M is the mass, D is the damping coefficient, K is the stiffness, and Fg is the electromagnetic force, which is computed from the FEA. So on the right-hand side, basically, is the basically force from the stationary model using a kind of parametric sweep optimization problem, where we vary the current from -2, 0, and 2. So basically, when the current is 0, the green line in the middle is the force by the magnet. So initially, just the force on the rotor side or the plunger is very minimal, because it's kind of symmetric and there is no force. Once it's start moving, then you will see some kind of force from the magnet only. So basically, the design idea here is that the magnet will have a sufficient hold force when it's to the extreme of the stroke, but has a minimum force when it's actually sitting on the initial position. So from the initial position, from 0, you're generating 10 Newton force by the coil, or negative 10 Newton. It's kind of symmetric, so it can go either way. But at the end, the total force is significantly coming from the magnet force. So that's the idea here. Now, this same, if you put into a dynamical equation, so what it comes out to be, it started about 10, and then there is some kind of peak points, which is slightly higher than the peak here. I think this is due to the aided motion on the actuator. So during the dynamic force, the force due to the velocity on it, that also have additional contribution to it. So that's why it's important that you not only test the force during the static operation, but also on the dynamic operations. So now, once we calculate those parameters, and then we also set up the optimization problem in COMSOL. So in this case, these are the parameters again: pole height, magnetic radius, parameter A and B. Those are the 5 parameters that we set up a optimization problem. We define the range, from lower bound, upper bound, based on our static simulations, and then we do a maximization of the force. And what we found was that the force, increased from 10 Newton to higher. The target was minimum 12 Newton, so we achieved this one, as you can see on the red line on the top. So now the same thing. Once the optimized parameters are introduced, we updated those parameters into the dynamic model, and then what we see is we turn on the current on the actuator. The position goes up. There is a overshoot here, as you can see on the oscillations. And there is a voltage on the coil. This is the velocity on the coil. It increases, kind of oscillates. And then the power. And then this is kind of how the force stamp out with the velocity term. So comparison before and after optimizations. The green line is before optimization, where we had a green bar here, only up to 10 Newton. And optimizations, we achieved slightly over 12 Newton force. And then also the spread of minimum maximum force here within this range is, decreased from 6 Newton to 5 Newton after optimizations. So this was the design target. We meet the sizing and also the performance as per the requirement. Again, the same animations, and this is the actual setup we did in 2DXE on the right-hand side, and the Revolve 3D version of the same. Right, so let's look into additional examples that are for plunger. So on the very left, we have a electromagnetic plunger. So what we have here is a plunger that is made of magnetic material. It is attached to some kind of stiffness and a damper mechanism. And then we have a slider, which is non-magnetic, which will allow this plunger to slide through. There is a coil, and then we have a housing that's made of magnetic material. So once we have a coil that's energized, the magnetic flux is generated on this flux, on the core, and it try to create a magnetic field path through this actuator. So due to the reluctance, so basically there is a reluctance force which is defined by the change in change in magnetics, or the magnetic gradient of the magnetic energy. So what we have here is basically, in this case, this is allowed to move up without any fixed block or position. It can go all the way up, no physical blocking. But on the right-hand side, we have the same scenario, exact same setup, but we have some kind of block that's holding it. So these are some of the blog that I wrote when I was at ComSol in my past job. So here is the link for those. And if you're really interested to learn about it, I think these are the good resources on how to set up these kind of actuators, but also set up an actuator where there is some kind of block in the very small limited space where you have to have that kind of design. Here are some of the animations of the magnetic flux on the left without a blocker, on the right with a blocker. So as you can see, the position it goes up. There is not much overshoot on this design compared to the previous one that I showed. The current is turned on to 4 ampere, and the position goes up. On the right hand side, same thing. You have the current that's turned on, but your position goes up, and you're reaching to the maximum point, and then it's kind of capped, stays there. And when you turn off, and it goes back, pulled by the spring. So this is the velocity profile on the bottom. All right, so please, make sure that if you have any questions, don't forget to type in the Q&A chat box, and I'll try to address them towards the end of the presentation. So let's take a look at some type of voice coil actuator designs. So basically, for voice coil applications, when the current flows through the coil, a Lorentz force is generated, causing the coil or the magnet to move. So, for example, we have two topologies here. On the top, we have a moving coil VCA. On the bottom, we have a moving magnet VCA. So the difference here is, if you look at it on the top here, we have a coil that is attached to some kind of coil holder, and it's inserted into the slot here. But the slot actually consists of a permanent magnet with the magnetizations. In this slide here, it's going up and towards, radially out and in. So basically, it's kind of sitting. The coil is sitting in the magnetic flux, uniform magnetic flux. So when you actually turn on the coil, then there is a force exerted on it, which is actually towards the right-hand side here. So the force is determined by the Fleming left-hand rule, where if the current is going into the plane and the magnetic flux density is going towards the y, then your force actually is towards the right-hand side in the positive x direction. So on the top, we have a coil that's oscillating or moving. But on the bottom design here, we have a coil that are fixed outside, but you have a magnet with some kind of, triangular or conical shape pole shoes attached to enhance the flux. So that actually move up and down as shown by the red arrow. So that's the difference here. Now, if you are into this VCA business, you'll see the literature. People have tried different combinations, as I've shown here in the at least 5 designs on moving magnet case, where we have a magnet north-south, with some pole piece to enhance the magnetic flux. The coil is attached and fixed, and there is a magnetic pole. So the design A has a single coil, but inner magnet with some magnetic materials enhancement. On the design B here, we have a dual coil. We have coil A and B, basically 1 and 2, as you can see. But the direction of current on those two are opposite. So what it does is actually, if the force from the one coil is attached or kind of attractive, the force from the other coil will be repulsive, so that the net effect will be doubled. But at the same time, there is some kind of clever design on the magnetic pole with a kind of conical shape here, so that will actually enhance or make the force profile more flat. On the third here, we have a single coil multi-magnet design. So now you can have magnets that can be arranged in an array, north, south, north. So it's kind of combination array in a Hallback fashion. And then also, as you can see, the magnetic core is designed to have some kind of triangular edge. So the other one is a single coil, and then now the outer magnet. So you have a magnet outside, coil inside, but still the magnet is oscillating. So this is one of the examples for camera lens zooming. The other example, you can have multiple coils, not as linearly arranged, but it could be in concentrically arranged, and many other combinations here. So so it looks like it's kind of art of designing. There are different options to choose from, and optimize it. So now the opposite here, we have a moving coil VCA. So we have earlier we have a moving magnet, but now we have a coil moving. So we have a coil attached to the mover, and then north-south magnet, and then magnetic material. Same thing here. We have a Hallback array combinations, magnet, bigger magnet, smaller magnet in the middle. So basically, we're trying to minimize the leakage flux on the center of the second coil. So there is a dual magnet. You can have a magnet on one side, left and right, and then basically you have the opposite direction. So you are trying to create a magnetic flux here, uniform, and then you have a big coil that's kind of oscillating here. The other one is we have three magnets kind of enhancing more flux. More combination, you can also have magnets on both sides so that you have more uniform flux in the space where the coil is sliding or the oscillating. It's called the dual Hall-Becker configurations. And then we have a dual coil, a dual magnet configurations, as you can see in configuration K. All right, so basically, there are different combinations. So, but why people choose one versus another one? So basically, the moving part for the moving coil, it has a less mass. So coil, when it has a less mass, it's faster response compared to the moving magnet. And the speed, when it's smaller, the speed could be higher. And the speed for the moving magnet, voice coil, is moderate. And then heat dissipations, again, there is a coil. There's some heat dissipations involved in it. And moving a wire, obviously, if there's a coil moving, then you have to have a flexible wire to allow it to oscillate. And then the force output, generally for moving coil, the force output is low, relatively lower compared to the moving magnet. And different applications, again, the moving coil used in the speaker, hard drives, pressure and flow control mechanisms. But on the moving magnet used for the applications where there is a high force demand, robotic actuations, and medical devices and so forth. All right, so a little bit about the demo example. So it is basically a plunger. We have a plunger here on the top, and we have a fixed coil on the bottom. And this is allowed to move as shown by the blue arrow here, up and down. We have a coil that's been energized. So instead of using the single coil core, we split it into 4 sections so that the loss or the whatever is the core loss or the hysteresis loss on this could be minimized. And here is, given that this is a symmetric model, we cut it into only model the 1/4 of it, as you see in the right. So here are some of the magnetic flux densities on the sections. The initial switching and after some switching time, where the gap is, there is a maximum gap and there is a minimum gap. So there is more flux in the core. Here are some of the losses on the core at different time. Let me switch into a software briefly here. All right, so this is the, first of all, we have the geometry here. As I mentioned, we are only simulating the 1/4 of it. There are different ways to do geometric parts in COMSOL. You can create parts and then import them here in the geometry sections, or you can directly import as an import file. But here it's created everything in COMSOL. So for those who are not familiar with the COMSOL GUI, I think I'll spend a minute here. So on the very right, we have a model builder where all the different nodes from geometry, parameters, physics setup, material setup, and the post-processing and the study types are available. You have the same equivalent here available on the ribbon button as in Microsoft products. But we have a settings window here in the middle, and we have a graphics window, the bigger one, where you see the result display or the geometry display. And then we have some sections with the messages, progress, and other updates on the bottom here. So if you don't know what to do, just right-click on your mouse, and then you will see the option. So this is how you do it in COMSOL. So basically, we have a geometry, and then we import this geometry here from the geometry part, and then we kind of customize it, by adding the outer geometries, because we are solving the electromagnetic fields. We want to make sure that we are also capturing the air domain outside it. So we have a material assignment here. This is the coil, and we have the magnetic materials here. Now, so what we have here in the physics side, so we have a magnetic field physics, and we have a coil that has been excited with 10 volts, and we have some parameters that define the filling factors, and then the parameters, the cross sections of this geometry, and divided by the cross section area of each of the tiny wires. So there are about 720 turns as per this filling factor and everything. So we have a cross section 1e minus 6, and that's pretty much for the coil. And under here we have a current coming in and going out from the other side. So it's a sector model, so we need to specify in and out of the coil. And this is the magnetic core. We define a nonlinear magnetic material here, defined by the BH curve, which actually comes from here. So this is our BH curve that's being used in the model. Then we add a force calculation node. So this is our plunger. We want to calculate what is the force on this. And we have a Gauss fixing, which is basically a numerical, for numerical convergence, because there is some numerical issue that need to be addressed, and it's kind of default. And we have a global equation. We're defining basically two equations, one for velocity and another for displacement. So in the velocity, there are some logical operations. I'll not go into detail, but here the idea is we have, if it touches the bottom, the velocity is reset to 0, and then the velocity will be determined by the force plus this, the spring constant time displacement divided by mass. And finally, we have, this is a little manipulation here. We have Ampere's law defined only for those thin regions, which is a gap between the core. So we define the permeability as 1 and the conductivity as 1. So we mesh this one. So given that the core is also conducting, so we are meshing, started the sweep mesh on this region here. There is a reason for this one, because we want to have this as a moving mesh feature, kind of deform region. So we want to have a uniform kind of sweep mesh so that it can squeeze or contraction or expansion whenever needed. Everything else is a tetrahedral, and then we have a boundary layer mesh on this. So what we have here is, so we have a boundary layer meshing on all the outer boundary of the coil, the core. And we started with the post-processing. I'm not going to solve it now, but sorry, I need to mention a little bit about the moving mesh here, physics. So since the domain are moving, so these two domains, the highlighted regions here, are deforming domains. So anything in between here will be either expanding or contracting. And we have this region here as a prescribed deformation. So it's not only the plunger, but also we're also moving the ear next to it so that it's easier for meshing. This mesh is not moved, but these two boundaries on the top and bottom are fixed because they don't move here. But this one follows the displacement that's being calculated by the global equation. So now in the initial, we calculate the coil geometry analysis, which actually is nothing but just to calculate the direction of current on this the coil. In the next one, we calculate the time-dependent studies, where we started from initial 0 to 1 seconds, but with some kind of finite values in between, because we want to know how the switching occurs. So on the result side, basically we have, once you compute it, we have some results already been post-processed here. So we're trying to show here there is a direction of current with a blue streamline, and the other region here is the meshing. And we have the magnetic flux density that's been plotted here at different time. So if we are interested just before the switching, there is the full gap here, the flux density is low. And when the gap is closed, the flux density actually will be larger. And similarly, we have the core losses at different time. This is just before switching. This is during the switching, and this is after the switching. So during the switching, there is more loss. And on the dynamic side, so what we can see here is that the blue line is the gap normalized, and the other one are the normalized and the current. So on terms of the dynamics, we have the gap blue and we have the current that slowly increases, reaches to the peak. And when the plunger is about to move, the current slowly, it actually draws less current now, slowly decreases. And the now next step, when it actually goes to the maximum, the gap, is minimal, then it slowly current actually increase again. Because during this transition here, the actuator is allowed to move so that it doesn't draw more current. But once it's fixed here, it again start to draw more current. So in terms of the losses here, the blue one is the total loss. The green one is the total loss. The blue one is the loss on the core. And similarly for the force, we see that there is, from 0 to about 2.6 Newton or 2.5 kilonewton force exerted by this one. So that's pretty much on the side. So it can be, so you can do optimization on different parameters, as I showed on the other example earlier. All right, so we have 13 minutes left. So I would like to run a little bit quick here. So comparison between the two here. So if you just use a solid block of core 1 versus split it into 4, the loss again, it can change. Here the maximum is 63.8 watt per centimeter cube, but it's reduced significantly to 24. So that's one of the design idea that you can manipulate. Not only for splitting, but you can also do the laminated core if you're interested in. So these are the same result that we discussed earlier in the software. So all right, let's look into some of the design tips here. Basically, so what we could do. So this is a little bit more complicated than the one that we just solved. But the idea here is, the dotted line here is basically without any current loss. So if you don't have any losses on the core, for example, if it's the ideal one, then the current will go to some value. And then, this is actually, started with the maximum force because you have a permanent magnet already attached. So it's kind of hold force. And then you are trying to release it against that force. So the plunger start to move quickly. But if you have a, no divided core, for example, this is the highest one. It keep draining more current, more and more current, and then it took a long time to generate that force, because significant amount of the current will be used as a loss. But you can, if you do a splitting this into half versus full, then you're actually decreasing the current requirement, but also increasing the performance, or it can generate the same amount of force early on that is speeding up the process. So there are different, the one that I'm demonstrating here is basically reducing the eddy current. But there are also different ways to increase the response time, by increasing the number of turns. You could also increase the magnetic force, but also you can use the bigger diameter of the coil that will minimize the resistive loss, right? But you have to make sure that you have enough space for that. And oftentimes, if there is a current rating that's not made for the wire, you can actually connect those two wires in parallel. Now, regarding the time constant, it's tau, which is the ratio of inductance to the resistance. You can always manipulate these values by either increasing the resistance or the inductance to change the electrical response time. The other idea would be, you can place magnets in different locations, increase the source sizes, but also, instead of putting the magnet here, for example, you can split into two smaller magnets on two regions here, or you could split on one side here, or you can make them parallel. Depending on the application, you can always, position the magnet in different locations to optimize. But I think we also have seen earlier that we can also not only put the magnets as is, but we can also put them in an array fashion like a Hallback array. For example, on the bottom example here. So the arrow, white arrow, indicating the direction of magnetization. So the other time, what my experience is that you design a plunger, but you obtain the maximum speed, but if the plunger continue with that speed, sometimes it does damage to the device. So you want to have the speed reductions at the end of the stroke. So in that case, you can always add, the damping, mechanical damper, or you can also do the short circuit on one of the coil that provide the electrical damping, or you can use some kind of hysteresis damping as well. So there are many ways to do it. So finally, so what the other one is, and if it's a flat plunger, the response will be like the plot one here. So it has a very high force, but it significantly decreases as you move on. But if you have a conical shape, for example, your force profile will be a little bit flatter, as indicated by the graph 2 here. But if you have some kind of proportional armature design, then you reduce that into a very flat profile like here on the third one. So it's, there are different ways to manipulate the magnetic path to achieve the maximum force and efficiency or the design target. So that's pretty much the end of my slides here. So in summary, basically we introduced what is electromagnetic actuators. We talked about different types. And I also showed you the workflow that I use for electromagnetic actuator in console. We talk about various optimization parameters with an example. I demonstrate the workflow of console with the power switch and share some of the design tips. So if you have any questions, please let me know. Let me look into the chat here. All right, so I have one question here. Basically, I mentioned that there is a nonlinear BS curve that can be built into the model. But the question is, how do you validate the accuracy of that input? So, or what are the validation criteria for such a properties? So, usually, if you are buying the core material from the standard suppliers, they will provide the BH curve, also a frequency dependent losses that can be directly incorporated into the console or any other FE software, for example. So, but just I think you need to find a material that has some kind of industry measurement or from the supplier side. I think that would be the best one. I mean, if you want to do validation yourself, there are different methods to do it, but it's very time consuming and cost as well. So I would recommend using the supplier that are reputed, but also there might be some literature from different organizations or publications that have some good reference for the materials that you'll choose. So once you have a graph, you can convert that into data and put it into console. All right, let's look for another question here. All right, so again, this will be recorded and you will get the the link with the recorded. So now the other question is, how will it impact the performance of the actuator by changing the wire size? So for example, if you have a wire gauge, let's say 22. So if you increase the wire size, meaning that you need a bigger volume or the space in the actuator design. And if you have that available, that means once you increase the size, the resistance will be decreased. So once resistance is decreased, means if you have a fixed voltage supply, it means you're getting more current into the system, right? Then that means the force will be directly proportional to the square of the current. So then your force will be increased. Once the force is increased, that means the speed of the plunger will be increased. So that's one way to actually get the speed up on the plunger. So the vice versa is true. If you decrease it, it increase the resistance, lower current, lower force, a lower speed. So I hope that answered your question. The other question is how do you model it in the motion in the 3D? So the magnetic field physics, they support only the kind of displacement that I did in the power switch model. Now, if you have more complex geometry, similar to this example, for example, if you have geometry like this, it's not possible just by using the form union in the geometry and using the deform mesh. So you would need a little bit more complex setup, which I would say basically, in that case, what you need to do is you need to combine the magnetic field physics and magnetic field no current physics and then moving mesh physics. So there are three physics you can couple, or you can directly use the rotating machinery interface in console that support magnetic vector potential as well as scalar potential formulation. The whole idea is that you have to separate the two stationary and a moving part as an assembly so that there is an identity pair between the two. So since the identity pair or that kind of coupling is not supported for the vector formulations, you have to have some kind of magnetic scalar formulations needed on that interface. So that's where, either you couple magnetic field no current physics with the magnetic field physics and manually do it, or already built-in coupling in RRM. Even though name is rotating machinery, it will support the linear motion as well by moving mesh features. So that's how I usually do for more complex actuator or linear machine design. I hope that answered your question. And regarding the meshing, also, if you have that kind of combinations, you have to make sure that the source and destinations are properly assigned, and so finer mesh on the destinations compared to the source. And also, if you have a symmetry or sliding interface, then you also have to have some kind of mesh that's been refined so that you have the field that coupling is done properly. But also in the periodic boundary condition, if you have some kind of periodicity in it, then you better use a copy mesh feature. I think some of the rotating machinery example in console actually has that feature, so I would encourage to use or refer to those. All right, that is the end of the session. So thank you everybody for joining this session. And if you have any question, please reach out to me, npaudel@veris.com. I will be happy to answer any other questions, and let's connect. If there is a need for modeling any electromagnetic devices and your organizations and you're struggling, then we'll be happy to provide our consulting services. And thank you again. Have a wonderful day.